Hello, everyone. Welcome everyone. Today we're going to talk about circular motion, and I'll just show you. If you're not familiar where to find the timetable for the webinars, if you go to our website, this is the list of webinars. Okay, so today is the 23rd, is the circular motion. Have you managed to download the assignment? When do we find out if we got in or not? Probably tomorrow. We are almost ready to release that information. Yep. So look out for an email tomorrow. So who's managed to download the assignment on circular motion? Do you know where to get it? No, no one. Hasn't anyone seen the assignment? So it's on the website in the assignments section. Sorry, we weren't clear. So physics assignment 2, and this is the assignment. And we're talking about circular motion. Okay. So then I have to start from the very beginning. Has anyone done circular motion? If you've done circular motion in school, type 1. If you haven't done circular motion, type 0. Okay. All right. Exciting. So I'll have something to show you. Good. We start. Yes, we do have a moderator today, and let's see chat. Okay. So the chat is moderated. Please be respectful. Yeah. All right. Circular motion. Circular motion is a really interesting topic because there's so much going on that is really not obvious. Okay. So, for example, let's look at a simple example of circular motion. So, vet circular motion. No, don't like that. Gravity, orbits. So let's say we have a planet going around the sun in a circle, of course. Familiar situation, right? Okay. If I ask you what causes it to move in circles, what would you say? What causes the planet to move in circles? Feel free to shout out if you have an answer. Gravity, yeah, causes the gravitational force. Look, the gravitational force causes it to go in circles. What would happen if there was no gravity? If we switch off the gravity, what would happen to the planet? We continue moving perpendicular to the orbit. Not sure what that means. Perpendicular to the orbit. Okay, so I can switch off gravity. Off. And now I press play. It goes in a straight line because that's what Newton's first law says. Newton's first law says if there are no forces, it keeps on going in a straight line. So yes, the thing is, it goes in circles because there's a gravitational force. And gravitational force is the only force. It's a force that causes it to change direction. So the gravitational force causes it to change direction. Circular motion is motion in a circle, and this force causes the force causes the Earth to change direction. Because if there was no force, it would be moving in a straight line. Good. This force has a special name. It is called centripetal force. Centripetal force. Now, centripetal is not a new type of force. It is the resultant of the other forces. But we'll get to that in a minute. The first thing I want to talk about is frequency, period, radiance, and angular frequency. So frequency is very simple. It's simply the number of revolutions per second. So frequency, see, the symbol is F. It's measured in hertz, and that is, frequency, hertz, and that's full rotations per second. Now, period, T, capital T, it's measured in seconds, is the time for a full rotation. Radian. Well, we'll get to a radian. If you know what a radian is, type 1. If you don't, type 0. Just so we are on the same page. Okay, so people know what a radian is. Good. All right. So radian. It's a measure. It's another unit. It's another unit for the angle. 1 radian is approximately 57 degrees. Angular frequency. Angular frequency, omega, is 2 pi f. So it's 2 pi multiplied by frequency. Basically, it's the angle through which through which angle swiped by by the moving object in 1 second. Let's see if we can, if there's an option here. Unfortunately, I don't see an option here. But anyways, let's let's say if this angle is 2 radians, for example, and the time is 1 second, if it is 2 radians per second. So omega is the angular frequency, is 2 radians per second. Angular frequency or angular velocity, which is the same thing. Angular, let's call it angular velocity. Sorry, angular velocity. Okay. Angle swiped by the moving object in 1 second. Does the angular velocity make sense to you on a scale of 0 to 10, please? 10, it makes perfect sense. And 1 doesn't make any sense at all. Okay. All right, so let me just explain further. Suppose you start moving from this point. You start from here. And after 3 seconds, you are here. After 3 seconds. And the angle measured in radians, for example, is 6 radians. I mean, obviously 6 radians doesn't look like that, but let's suppose it is. And then your angular speed, angular velocity, is the angle that you turn 6 radians by 3 seconds. So that is 2 radians per second. That means that the moving object swipes through an angle of 2 radians every second, which is approximately 114 degrees per second. Does that make sense now? On a scale of 0 to 10 again, please. Okay, lovely. So we got there. So this is just the meaning. Angular speed is a very useful thing to talk about. Why is it useful? Well, for example, why is angular speed useful? Let's take a wheel, for example, and it is rotating. The thing is that if the edge of the wheel is spinning at, I don't know, 10 meters a second, other parts of the wheel don't. So for example, this point would probably go like 6 meters per second. The closer you are to the center, the slower you move. And the further you are from the center, the higher your linear velocity. Linear velocity gets bigger as you move away from the center. center. The further you are from the center, the faster you move. But the angular velocity is the same for any point on the wheel. Okay. So there's a question about the assignment. Can you please send email to compos at physics UK, and we won't check. Please, yeah, the same text. So yeah, for any point of the wheel, the angular velocity is the same. However, and there's a link between linear velocity, which is v, which is the normal velocity, and the angular velocity omega. V is equal to omega multiplied by the radius, which is the distance from the center of rotation. That's a very useful formula that we will be using as well. Okay, so what other formulas are there? It is in a similar way. I mean, moments are very linked to angular speed, angular velocity. Yeah, and I mean, there's a lot of when you start to study rotational mechanics, which we didn't. We were thinking of adding rotational mechanics, but we didn't really. Yeah. So the other thing is the other formulas that you need to know is that the time period is 1 divided by frequency. You probably know this from waves. Then you have the angular velocity is 2 pi f. Also, this is 2 pi divided by t. Very useful formula. And I think that's it for now. Okay. How big is 3 radians when expressed in degrees to the nearest whole number? When I said that 1 radian is about 57 degrees, if you want to convert radians into degrees, you need to multiply by 180 divided by pi, because pi radians is 180 degrees. But you already know this, so I won't. 180 divided by pi times 3, 172 degrees. So 3 radians is approximately 172 degrees. Okay. How many radians are there in 90 degrees? Well, 90 degrees, you want to convert to radians, so you multiply by pi over 180. So that gives you pi over 2 radians, which is approximately, well, 3.14 divided by 2. So it's 3.14 divided by 2. That's 1.57 radians. Okay. Complete the questions in the frequency. In the table, sorry. Complete the questions in the table by converting the units. So let's say if the time period is 0.5 seconds, that means a full rotation takes 0.5 seconds. That means in 1 second, you do 2 full rotations. That means that the frequency is 2 Hertz. Okay. The angular velocity If you do 2 full rotations, one rotation is 360 degrees, but that's also 2 pi, 2 pi radians. 2 full circles, 2 full circles. And that is 2 pi multiplied by 2 radians. That means it's 4 pi radians per second. 4 pi radians per second. Okay. Revolutions per minute. Well, you have to multiply 2 hertz by 60. So it's 2 times 60, which is 120 RPM. So this is a common unit to use in machinery, because you don't always want to know how many rotations per second. You're more interested in how many rotations per minute, because it's a more meaningful value. Right. So yeah, in a car, when you talk about a car, the engine is the frequency of rotation of the engine is given in RPM. Okay, what if the angular frequency is 3 radians per second? What is the frequency? What is the time period? Well, remember we have angular velocity is 2 pi f. That means frequency is omega divided by 2 pi, which is 3 divided by 2 pi, which is approximately 3 divided by 2 pi, 0.477 hertz. So the answer is 0.477 hertz. The time period, well, we know that the time period is 1 divided by frequency, which is 1 divided by 0.477, which is approximately 1 divided by also is 2.09 seconds. And revolutions per minute, well, it's just frequency times 60. So it's 60 times 0.477, which makes it 60 times 28.6 RPM. 28.6 revolutions per minute. Is this making sense to you? Is there anything you don't understand here? Okay. All right. So example 1. Oh, this is from the assignment. I've modified it slightly. A wheel of radius 1 meter is rolling without slipping at speed 2 meters a second. Find the velocities of A, B, C, D, E, F. Okay. So here we have 2 separate motions. We have the translational motion, so the whole wheel is moving, but also it is rotating. So 2 types of motion, 2 types of motion. First is the translational motion. And here, all parts of the wheel are moving in the same direction. And 2 is a rotational motion. So here, different parts of the wheel move at different speeds. So like this, the center is not moving. So you have like this, like this. Now this part of the wheel is moving backwards, like this, like this. So basically, some parts of the wheel are moving to the right, some parts of the wheel are moving to the right, the left. However, this is all 2 meters a second, and this is 2 meters a second. Now, the bottom one is minus 2 meters a second, and this is 0 meters a second, 2 meters a second. So if you want to add the two, you have to add the translational motion and the rotational motion. And you get something like this. The 2 meters a second at the top of the wheel plus 2 meters a second here makes the total velocity 4 meters a second. So the top of the wheel is moving at 4 meters a second. And that makes perfect sense because it has to move faster than the wheel itself. The center of the wheel is 2 plus 0. So that's 2 meters a second. So the whole wheel is moving at 2 meters a second. And that means that the center of the wheel is moving at 2 meters a second. The top of the wheel is 4 meters a second. And the bottom of the wheel, so it's 2 and minus 2, so it's 0. The bottom of the wheel is stationary. And that is true. Yes, because the bottom of the wheel has to be stationary. It is in contact with the ground. There's no slipping. So the speed is 0. So at B, the velocity is 0. E, the velocity is 4 meters a second. C, it's 2 meters a second. B is halfway between A and B. And you can use the linear approach and to say that it is 1 meter per second. Okay, so this is 0 meters a second. Okay, that's the easy part. That's 4 meters a second. What about D? Well, point D. The whole wheel is moving at 2 meters a second to the right. But also, D is moving up 2 meters a second. So the total velocity is like this. And if you use Pythagoras theorem, this is going to be, somebody quickly can do this, Pythagoras. Two root 2, thank you. 2 root 2 meters a second, yes. So the point D is moving up at 2 meters a second, but also the whole wheel is moving to the right at 2 meters a second. And that means that the total speed is 2 root 2 meters a second at a 45-degree angle. So if you look at D, D would, at this moment in time, would be moving in that direction. And I think it's reasonably easy to convince yourself that, oh, yeah, that this is true. Okay. The next part is F. Now F is trickier. Point F. So we are considering the two types of motion. Once again, we're considering the linear translational movement of the wheel. So that's 2 meters a second. And now F, it's a 45-degree angle. And it is moving like this, which is also 2 meters a second. You need the total, and this angle is 45 degrees. You need the total, so you need to use parallelogram rule to find this. Okay. Well, you can use the cosine rule here. or you could use vectors. I'm going to use vectors here. I'm going to write down that this vector is 2, 0, and this vector is root 2. Yeah, it's root 2 and root 2 because it's the total is 2, so root 2 squared plus root 2 squared is 2. Okay, yeah, that makes sense. With the square root. Okay, so now this vector is 2 plus root 2 and root 2. So the speed at f is square root of 2 plus root 2 squared plus root 2 squared, which is 4 plus 2 times 2 root 2 plus 2 plus 2. That's 8. 4, 2, square root of 2 plus root 2. Something. It is something. 4, yeah, 2. And then you just calculate 2 root 2 plus root 2. 3.69. 3.6. 3.70. 70 meters a second. Which makes sense. Yeah, it's more than the middle, but less than the top. The top of the wheel is the fastest part of the wheel. And okay, the angle. The angle is obviously going to 22 angle. Theta is 22.5 degrees. In the assignment, you will need to do that, but not for 45 degree. You will need to do it for an arbitrary angle. So let's say angle alpha, and you need to work out the speed in terms of alpha. Problem 3. A stone flew off at point F. How high will it reach? So we already know the velocity of at point F. So this is 2 plus root 2 square root of 2. We also need to know how high it is at the moment. So we need to find where it is at initially. The initial height, h0. Initial height. And which part, if I want to find the maximum height reached by the stone, which do I need to take? The top or the bottom? The bottom. I need, because that's the vertical component. That's the vertical component. Initial height. Square root of 2. V is initial velocity. And yeah. All right, so we need to h0. So this is 2. Oh, what is the radius of the wheel? I don't think we know the radius of the wheel. A radius 1 meter. Okay, radius is 1 meter. 1. And this is 1. So that's root 2 over 2. So from, well, using Pythagoras actually, h0 is 1 plus root 2 over 2. And then max height. Max height. So time to reach max height. Time to reach. Oh, okay, let's do suvat. Let's not worry about it. Suvat. Displacement is question mark. Initial velocity is √2. Final velocity is 0. Acceleration is minus 10. Let's keep it simple. And t is, well, we don't really know. So we can use s is equal to 2as is v squared minus u squared. U squared. Okay, so s is v squared minus u squared divided by 2a, which is v squared is 0 squared minus 2 divided by 20, which is 0.1 meters. Oh, that's interesting. So it will reach a maximum height of 0.1 meters above the starting point. So max height reached is h0 plus 0.1 meters, which is 1.1 plus √2/2 meters. Okay, that's it. Okay. Centripetal acceleration. Well, we've seen before that in order to move in a circle, there must be a force towards the center of the circle. In order to move in a circular path, you need a force towards the center. Now, it is important that it is an unbalanced force. Okay. This force is known as centripetal force. But if there is an unbalanced force, that means you are accelerating. And you have to be accelerating in the direction of that force. That means your acceleration is towards the center. But mass times acceleration is equal to the resultant force. That's Newton's second law. If there's a force, there is an unbalanced force, there must be an acceleration. That's the first piece of the puzzle. If you're moving in circles, that means that something is pulling you into the circle. And there must be an unbalanced force. If there's an unbalanced force, there must be an acceleration. So you have to be accelerating towards the center. This acceleration is known as centripetal acceleration. So if you're moving in circles, you're accelerating, and that acceleration is towards the center of the circle. That is counterintuitive. That does not go well with your everyday understanding of life. So wherever you are, you're accelerating towards the center. Acceleration, acceleration, acceleration. How does that even make any sense at all? Like, why is there an acceleration towards the center? So if you're here, there's acceleration this way. If you're here, the acceleration is this way. If you're here, the acceleration is this way, and the acceleration of this way. And maybe in the GCSE course of physics, you were taught that direction is changing. Yes, direction is changing, but why is it towards the center? Why is it not in any other direction? Maybe you were taught that the centripetal acceleration is actually equal to v squared divided by r. It's a very useful formula which we will use today. V squared over r. This is the velocity divided by squared velocity, squared or speed squared. When you square it, it doesn't matter if velocity or speed, because you square it, it all becomes a scalar. V squared over r, and r is the radius of the circle, of course. But how does that even make sense? Why is it towards the center, first of all, and why is it v squared over r? So let's try to work that out. So here we have a diagram. At A, the velocity is v1. And at B, the velocity is v2. And you can see that the velocity is clearly changing. The change in velocity, delta v, is the final velocity minus initial velocity. And if you apply the rule of subtraction of vectors, you will see that v2 minus v1 is this red vector here, which is indeed towards the center of the rotation. Does this diagram, do you understand this diagram? On a scale of 0 to 10. Initial velocity, final velocity, and this is change in velocity. Change is final minus initial. So, all right, so I'll try to convince you. So delta v, by definition, the change in velocity, is the final velocity minus the initial velocity. So this is the final, and this is the initial. I hope I don't have to convince you on that. I can write down that v2, I can rearrange that and make v2 is equal to v1 plus delta v. So what is v1? Well, v1 is this. This is v1. Delta v is this. Delta v. And this is v2. Because v2 is v1 plus delta v. Do you see that? Do you see that v2 is delta v1 plus delta v? These are vectors. And therefore, yeah. So I hope this is more convincing. Is it? Please let me know. Okay. Okay. So delta v is the change in velocity, and acceleration is the change in velocity divided by time. Time is a scalar. Therefore, acceleration has the same direction as the change in velocity. So change in velocity, so acceleration has the same direction as the change in velocity. Change in velocity has a direction towards the center of the circle. Therefore, acceleration is also towards the center of the circle. And that's the second piece of the puzzle. I hope I convinced you that there must be a force. And if there's a force, there must be an acceleration. And now I have shown you that the direction of that acceleration is indeed using the change in velocity vector. towards the center of the circle. And yeah, and in the assignment, we show that. Okay, well, let's do that. Let's do that. The change in angle, here. So let's move that to the side. The change in angle. Remember, from the definition of angular velocity is change in angle divided by change in time. And from here, I can express delta theta as omega multiplied by delta t. Now, if you look at this triangle, you can use the cosine rule. Yikes. Well, yeah, you can use the cosine rule. Cosine rule. That delta v squared, the opposite side, is equal to v1 squared plus v2 squared minus 2 v1 v2 cos delta theta, cos of this angle. But this is v because the speed has not changed. It's the direction that has changed. But here we don't consider the direction. We consider the speed. So it's delta v squared is v squared plus v squared minus 2v squared cos delta theta. And then this is 2. Delta v squared is 2v squared, open bracket, 1 minus cos delta theta. Using the small angle approximation, small angle, because we can assume that delta theta is a small angle. Summation. Cos x is approximately 1 minus x squared over 2. That's the small angle approximation. And that means cos delta theta is approximately 1 minus delta theta squared over 2. And then I'll plug that in. So delta v squared is 2 v squared 1 minus 1 plus delta theta squared over 2. 1 cancels, 2 cancels, and I get delta v squared equals v squared delta theta squared. Okay, so from here I can express delta v is equal to v times delta theta. So delta theta is delta v divided by v. Okay, so I now plug that into here. That means I have delta v divided by v equals omega delta t. Ah, yes. And now I divide both sides by delta t. I guess delta v divided by delta t equals v omega. But remember that omega, so v is omega r, that means omega is v divided by r. And I plug that in, so delta v over delta t, which is acceleration, yeah, equals v multiplied by v over r, which is v squared over r. And this is the formula, a equals v squared over r. That's how you obtain the acceleration, the centripetal acceleration. Okay. It's one of the ways. There are plenty of other ways. Similarly, you can do the other way around. V equals omega r. That means you can replace that. So acceleration is that. So acceleration is v omega, which is actually omega r times omega, which is omega squared r. So acceleration is omega squared r. That's another formula for centripetal acceleration. So if you're moving in a circle, your acceleration is towards the center, and it's equal to v squared over r. Okay. I really hope I managed to convince you of that this is true. Problem 5. It's funny today because I've written this problem, and then I asked somebody. I asked one of our tutors, what should I put into the assignment, into the webinar, and they said, "Oh, you need to put like 5 examples of circular motion and identify the centripetal force, like word for word." Word for what I've written. So that means it's a good question. When do we get our assignment results? There's a question. Probably tomorrow. If everything goes smoothly, it is tomorrow. I didn't give 5 examples of circular motion. Identify the centripetal force. Is the motion uniform? So, all right. So I'll start with an easy one. Mass on a rope doing horizontal circles. Okay. First, mass on a rope making horizontal circles. Oh, actually, it's here. But anyways, so mass on a rope, and it's going in a horizontal circle. Okay. This is the radius of the circle, of course. This is the radius of the circle. What are the forces acting on the mass? What are the forces acting on the mass in this position? Weight, very good. Weight. And there's a tension force. Tension force. Now, if you were to add the tension and the weight, you would get a force towards the center of the circle, which shouldn't be surprising. So the centripetal force is the total of weight plus tension as vectors, of course. So weight is a vector, tension is a vector. This is the centripetal force is the weight plus the tension Try to remember, it's going to be tough, but the centripetal force is always the resultant force. It is not something new. It's not a new type of force that you haven't studied before. No, it's just the resultant of the other of the remaining forces. And that's it. Do you think this motion is uniform? Uniform means with a constant speed. Constant speed. Yes, it is. Therefore, uniform. Uniform circular motion. Motion. Does that make sense? Tool. Net energy. Okay. This is circular motion. So what are the forces acting on the skateboarder? Ignore friction. Let's not do friction. Thank you for the suggestion. Weight, yes. The weight. And the normal reaction, of course. The normal reaction is going to be reasonably small. Normal reaction. And the centripetal force, in this case, is the normal reaction plus the component of weight in the direction of the normal reaction. Okay. So here, if we split the weight into two components, let's call this theta. This is W cos theta, is W sine theta. So the centripetal force is the normal force plus W cos theta. So it's the component of the weight towards the center. And what do you think this component does? What do you think that W sine theta does to you? No, inertia. Inertia is not a force. At least it's not a force in our frame of reference. So we will not be studying the inertia force. Please don't use the inertia force. if you really want to make your physics teacher angry, say inertia force. If you want to make them even more angry, say centrifugal force. I think nothing makes a physics teacher angrier than the phrase centrifugal force. If you have good relations with your physics teacher and they can and it's okay to joke with them, ask them about centrifugal force. Uh, let's see what they have to say about it. What they can say about it. We do not use centrifugal force for good reasons, because this is an imaginary force which only exists in non-inertial frames of reference. Yes, and the same for inertia force. Now, this force slows the person down, which makes perfect sense. Yeah, they're not moving at constant speed. They're slowing down because they're going uphill. This component is slowing the skater down. And these two forces cause the skater to move in circles. Cause to move in circles. In circle. There are no other forces. There's no centripetal force. There's never centrifugal force. Now, is this a uniform circular motion or not? Somebody tell me. Is that uniform or not? It is not uniform. Why not? The person is not moving at constant speed. The speed is changing. Speed is changing. Of course, the person is slowing down as they go uphill. Look, if I do the kinetic energy, the speed, and I restart them, the speed first increases, now decreases, and then increases again. Okay. So quite nice. Lovely. Okay. All right. So somebody else give me an example. 3. Think of an example of circular motion. A motorbike driving up a curved wall sideways. Okay. Motorbike. In a. Is it called a death pit? A wall of death. So yeah. Wall of death. Yeah. All right. What else? Planets in orbit. Yeah, that's a good one. Planets in orbit. We already have this one. Planets. So that's 5 examples. I'll just want to add one more, which is a very important car going over a curved bridge. Physics. Okay. Image. Okay, so here, that's an old pendulum. Yeah, pendulums, that's a good one actually. Would a hammer throw be one when you spin and don't fall over? Ah, hammer throw, yes, of course. Hammer throw. Throw. Hammer throw. Pendulum, yes, definitely a pendulum. Ferris wheel, okay. Pendulum. Pendulum. Yes. And a Ferris wheel. And I'll stop here. Ferris wheel. Ferris wheel. Ferris wheel is actually quite sophisticated in terms of the force. So yeah. Motions in a tornado, of course. Yeah, circular motions. Right. Let's identify the force that causes this circular motion. Because here you have 3 forces. You have the normal reaction force from the ground. You have the mg force, the weight of the car. But you also have a friction force, the force of friction. Because these forces are balanced, so the friction force is the centripetal force. Friction is centripetal force. Okay. It's not, once again, it's not a new thing. Centripetal force is not something new. It's the thing that's already there. It's already existent. You just need to identify it. Okay. What's this here? What is the centripetal force? What acts as the centripetal force? Or for the motorbikes? Yeah, that's a very good image. Yes. Yes, thank you. Mila, thank you. That is correct. It's the reaction force. It's the normal reaction force. Look, you have the reaction force from the wheels, and that acts towards the center of the circle. So the normal reaction is the centripetal force. Okay, there are also other forces, of course. There's friction, the friction that prevents them from sliding off. So there's friction upwards, force of friction. There is there's the normal reaction force, of course. What else? Oh, yeah, that's it. That's it. Friction, normal reaction. Oh, the weight, of course. The weight. So the weight is actually supported by the friction force. Sounds a bit paradoxical, but that's how it is. The weight, they're not falling down because of the friction force with the wall. The planet in orbit, so the gravitational force, is the centripetal force. That's an easy one. Now this one, that's interesting. So when the car goes over a bridge, which is shaped like this is the radius. So this is yeah. So we have the normal reaction force, and we have the mg force. And which one is bigger? Which one do you think is bigger, the normal reaction or the mg, or are they the same? Yes, people are sending their messages to me directly rather than into the chat. I'll try to read them out. What is the centripetal force here? Is the imbalance between mg and n. Okay, so mg is actually greater because it's accelerating downwards, right? It's circular motion, so it's moving in a circle. That means there must be an unbalanced force downwards. It's moving in circles, there must be an unbalanced force downwards, and the centripetal force is mg minus n. So mg is pulling you towards the center and n is pushing you away from the center, but mg is bigger. When you're going over a bridge like this, mg is going to be bigger. If you go here and you look at the forces, there's the same two forces, n and mg. But this time acceleration is upwards. That means n is bigger than mg. Acceleration is up. So the centripetal force in this scenario, the centripetal force is the normal reaction minus mg. Okay. We'll get to that. We'll get to that in a minute. The hammer throw. What is the centripetal force in the hammer throw? Somebody. The tension. Yes, of course. Thank you. Tension is the centripetal force. For the pendulum bob, it's the same situation as for the mass on a rope. There is the tension, and there's the mg, and this is theta. So the centripetal force is tension minus mg cos theta, because there's a component of mg that acts against the centripetal force, against the tension. So the centripetal force is the resultant force towards the center of the circle, which is that. Centripetal force is the resultant force towards the center of the circle. Good. The Ferris wheel is actually quite nice because so here the cabin is hung from the top. So that means that there is tension here of the hanging place where it's hung. And there's the normal reaction. Oh, sorry, mg. Now, there is a very, very slight imbalance of the two forces, which gives rise to a centripetal force. The imbalance is so small that it's really hard to show it. So mg is not equal to tension, although very close. The imbalance results because it's the resultant force results in a centripetal force. It's easy to see at the top. At the top there's the tension and there's mg, and mg is slightly bigger than the tension. That's why there's a resultant force downwards. At the bottom the tension is slightly bigger than mg. The tension is slightly bigger than mg. This is a strange Ferris wheel. Is it going underground? Because if you continue this line, it sort of has to go underground. Okay, it has an underground section. Yeah, or I mean. Anyways, I hope that makes sense. I hope that makes sense, and I hope you've got a feeling for the centripetal force. So let's come back to the mass on a string. Right, mass on a string doing uniform circular motion. Find what? Find omega. Okay, find omega. Okay. Let me just double check. Find the frequency. Okay. No. Find the angle. Find alpha. Okay. Find the angle if you know the frequency. If you know the omega, if you know the length. Well, as we did before, we'd show the forces. So there are two forces. So there's the tension and there's the mg. Now, the mass is not moving up or down. So if we resolve the tension into components, this is going to be, this is alpha. This is T cos alpha. And this is T sine alpha. So T cos alpha has to equal to mg. T cos alpha equals to mg. Vertical forces are balanced. Forces balanced. Now, this force is the centripetal force. T sine alpha is the centripetal force. But centripetal force is equal to mass times centripetal acceleration, which is mass multiplied by v squared over r. That means T sine alpha is equal to m v squared over r. Okay, not good enough because we need omega. Okay, so it's going to be m omega squared r. That's better. M omega squared r. Good. And I just copy this T cos alpha equals mg. Now I'm going to divide the first equation by the second. So the first divided by the second. So T sine alpha divided by T cos alpha equals m omega squared r over mg. M cancels, T cancels, and we got sine tan alpha. Tan alpha is equal to omega squared r over g. Now, the only thing that we don't know is the radius, because the radius of the circle. Well, we actually do, because the radius of the circle is linked to alpha and r is equal to L sine alpha. So tan alpha is equal to omega squared multiplied by L sine alpha divided by g. Tan alpha is sine over cos, so sine cancels. So cos, okay, sine alpha over cos alpha equals sine alpha over cos alpha. Sine cancels, and we get cos alpha equals g over omega squared L. And that's the answer. I found the angle. I don't need to, in a question like this, you don't necessarily have to say that alpha is arc cos of that. Of course it is. If you find the cos of the angle, that means you found the angle as well, because there's only one possibility. The angle has to be, there's only one angle with a given cos between 0 and 90 degrees. And it's obviously the angle is between. Right. A car is going over the bridge. What is the normal force? So let's say the car is going over a bridge, and there are two forces. There's the normal reaction force, and there's the mg force. And we know that the acceleration is downwards, and we know that the acceleration is v squared over r. So the resultant force is equal to mg minus the normal reaction force. And that means mass acceleration is mg minus n. You can view the whiteboard at any point. Okay, A equals mg minus n. A is v squared over r, so it's mv squared over r equals mg minus n. So n is equal to mg minus mv squared over r. So normal reaction force is, if the car is stationary, let's if v is 0, then means n is mg, which is what we expect, right? If v is large, what happens to n? Like if v becomes really big, what happens to n? Imagine mg is fixed, right? But you can increase the speed. If you go really, really fast, what happens to n according to this? It becomes negative. It becomes negative, but that means that the road is pulling you down, but that's not possible. Right? If n is large, n becomes 0. So lose contact. So the car takes off. The car flies off the bridge. Yeah. Okay. Lose contact. The same. There's a question about the rotating Earth. So if you're standing on the planet Earth and you're standing at the top, you're not moving. The Earth is rotating, and anti-clockwise. Oh, it's moving from west to east. It's rotating. If you're standing at the top of the Earth, that's standing at the North Pole, there's a question like that. If you're standing at the North Pole, your weight is equal to your normal reaction force. But if you're standing on the equator, you have acceleration towards the center. That means your mg is greater. So at the equator, so at the pole, at the equator, you're accelerating towards the center because you're spinning with the Earth. So your centripetal force is your mg minus the normal reaction force. So normal reaction force is mg minus centripetal force. So your normal reaction is mg minus mv squared over r. So on the equator, you will weigh less. Well, your weight would be the same, but your normal reaction would be different. That means if you stand on a set of bathroom scales, you have a lower reading. Okay? If you weigh yourself on the equator, your weight would be smaller. Okay. Finally, this is a question that didn't make it into the assignment. And it's probably my favorite question. My favorite question of all. It's really hard. It's a difficult question. I don't want to do the whole thing, but I want to do part of it. So a small mass is on top of a sphere and it starts sliding down. So it starts sliding down, picks up speed, of course. Why is it picking up speed as it slides down? Not quite. Normal reaction force does get smaller, but that's not the reason. Why is it due to the mg? Yes, ideally if you could type it in the chat because it becomes more lively. Otherwise, people don't see what you're saying. Due to the mg, yes, but can you still elaborate? Like, what do you mean due to the mg? What does mg have to do with the increasing speed? Which do sorry. So if you take like this, the object is moving, it accelerates due to gravity. Of course it accelerates due to gravity. Yeah, I mean, look, I put the dog on top and I let go. And you can see that. All right. So the point is that at some point, the dog will lose contact with this sphere. So you can see that at some point here, you see the dog has left the surface. But you could also, I hope you've seen that the speed is increasing. So why is the speed increasing? Yes, it's accelerating due to gravity. Can you think of another reason? There's no friction at all. So we assume we live in a world where with no friction. Think of energy. Look, think of energy. You have a conversion from potential energy to kinetic. Yes, of course. Potential energy converted to kinetic energy. That is probably the easiest explanation. Of course. So you pick up speed. Speed is increasing. Speed increases. Increases. And then at some point here, when the angle is this is theta, you can draw the forces acting on the mass. So there's the mg. There's the mg force. It's downwards, and there's the normal reaction force outwards. And if you resolve mg into components, you have two components, one towards the center of the circle. So this is mg cos theta. And there's a component here, so this is mg sine theta. So this is the component of mg that causes you to accelerate. So this increases the speed. Whereas this causes you to move in circles. So the centripetal force is mg cos theta minus the normal reaction force. But the centripetal force is mv squared over r equals mg cos theta minus the normal reaction force. When it loses contact, n is 0. That means mv squared over r equals mg cos theta. You cancel the m. So if you're looking for the angle, cos theta equals v squared over rg. So this is the angle at which it loses contact. And then, of course, you can find the v from 1/2 mv squared equals mgh. So v squared equals 2gh. You can use that as well. All right. So I think I will finish here. Thank you. Thank you for your attention. I have done more webinars on circular motion, and I've actually done a webinar this year. So if you go to our YouTube channel, you will find the playlists. You need to go to the year 13 playlist if you want to watch the other webinar. And there's orbits. Webinar 1 is circular motion. So I'm going through similar questions. And yeah, so we have the same topic in year 13. So yeah, next year you're not going to do circular motion. Next year there will be a different topic. So don't worry, we're changing. Basically, we took the year 13 assignment, we modified it and put it into year 12. That's what happened. And now next year you'll have a brand new assignment for year 13, and you won't be doing circular motion. All right, enjoy the assignment. Please download it from our website. We'll try to send everyone emails tomorrow, whether you got in or not. It's very difficult. This question got removed because it is a very difficult question. It would be unfair to you. But you can have a go at it. Okay. All right. Okay. Yep. See you all. When do I see you? Webinars. The next webinar is on the 6th of November, so in 2 weeks' time. All right. See you.